Okay, hello. I'm Josh Borrow. I'm a systems architect at the University of Pennsylvania, mainly working on software for the Simons Observatory experiment. And today I'm going to give a little brief overview of some software development best practices. This is primarily aimed at physics kind of starting graduate students or various people within physics who are kind of getting started in software development, and especially those who are transitioning from kind of writing software just for themselves to writing software in like small teams. I'm going to assume that you have some knowledge of Git and GitHub workflows, so things like branches, pull requests. If you don't kind of understand those, you'll still get something out of this, but you'll miss a little bit, and I'd recommend going and looking those up. And most of the discussion in the talk is mainly going to be relevant towards people working in the Python programming language, but there's a lot of concepts in here that are really general. So the title here is how to not have your teammates hate you. And that is effectively the goal of this presentation, is to teach you how to develop software in a way where you're not stepping on the toes of other members of your team, and you kind of know that no one's stepping on your toes. So let's start by looking at what the problem is. So let's imagine we're working on a piece of software in a small team. So how is it possible for us to all work on this software together without, breaking each other's code and making sure that, everything works together? So this is a small team that I'm part of. It's a simulation code for astrophysics. So you can see here that there's 30 contributors to this package on GitHub. I'm, the 7th largest contributor of code to this repository. So I'm not, the biggest contributor to this. But, working in these small teams, you really have to be very careful about exactly how you work with the code in a way where all of these 30 people can work together and be productive together. So the goals really for any piece of software that you're going to share with other people is that it's accurate. That's always the goal in software, right? Is my software has to do exactly what I say it does. It may do other things as well. That's also not great. But if it doesn't do what I say it does, that's really bad. You can consider something like a numerical integration function. If that numerical integration function gives you the wrong answer, then it's effectively useless, right? So we have to make sure that the code is accurate. It should be easy to use. This is somewhat kind of obvious, right? It's always nice for code to be easy to use, especially if you're working with other people and expecting external users to your code. You want it to be easy to use because otherwise no one's going to use it, right? They're going to give up and go somewhere else for their code needs. Just place myself all the way up here for now. So of course, it's always good if code is fast. So speed is of the essence. And it would also be really nice if it was easy to develop and add features to the code. So we're going to go through with some techniques of how we can make sure all of these concepts are brought together and are applied to the code. So how can we ensure that a code is accurate? In physics, it's very common to take your code and compare it to some kind of known result. So this is a paper that I wrote a little while ago for a numerical hydrodynamics scheme. And this is a simple blast wave test. Basically, can the code do explosions? This dashed line here, this is an analytic solution, and the dots are the particles in my simulation. And so kind of shows, okay, it's a relatively accurate scheme. There are some kind of oddities like this wiggling here. These are kind of well understood parts of the numerics. But this answer is kind of fuzzy, right? If I go and change the code and this answer moves around a bit, right? Because it's not exactly on top of the analytic solution and we would never expect it to, there's always going to be errors in numerical schemes that are kind of fundamental. How do I know that by changing the code and changing the answer a little bit, I haven't broken something, right? It may pass on this test, but if I go and run something else, it may fail. So this is a really fuzzy test. And so in development, this is not very useful, right? Also, these kind of full scale tests, they require a significant amount of effort, right? I have to go and run this simulation. I have to make the figures. I have to look at them. I have to discuss with other people about whether they're good enough or not. And so what we really want is a pass-fail test. So this is not always possible within physics, especially, when you consider the final cases, right? Like it's not really possible to write a pass-fail test for that explosion. I can't, that's always at some level going to be subjective because it depends on the errors in the numerical scheme and the errors in the kind of underlying approximations that we made. But certain code paths along the way, we can do pass-fail tests for. And so if we break our code up into lots and lots of little pieces, we may be able to test them all individually. And so we may be able to test the entire code. So that would, if they all pass some kind of pass-fail test, we will be more confident that the code is doing what we say it does. So this is an example from a real production system that I'm working on at the moment. So this is a test function in Python that attempts to test this function, log2database. So what it does is it sets up some state. So it takes in these parameters to the function. We'll see what these are in a minute. So these are a test server to interact with and a test ORM. So this is something to do with the database. And then we import the function here. And inside what I do is I then call the log2database function a few times with different parameters. So log2database, what it does is it takes an error of some severity, some category with some comment, and it sticks it in some database, and that database is given by this session here. And so what this function is really trying to test is, okay, I say that log2database does this. Does it really do this? So I call it a bunch of times. And then what I do is I close that database session and I go and get a new session in the database. And I go and ask, okay, hey, did all that stuff get in there? So I query the database for the errors. I say, okay, are there 4? I put 4 in. This is what the assert keyword does. If this statement is not true, assert will raise an exception. So for every error, I check that the message is test because that's what I put in there. I check that it's not been cleared. And of course, check that the cleared time is not set as well. If it's not cleared, then it won't have a cleared time. And then I go and I check individually, okay, are the categories all correct? And by doing this, I increase the confidence that I have in log2database doing what I think it does, right? I actually went and I said, go and put something in the database, and I checked that it went in there. By doing this check, it increases my confidence that it will work when I go and run this for a real case. Now, testing is not a magic bullet. It doesn't guarantee that the code is correct. It just increases your confidence. You can spend years and years and years writing tests and you've missed some edge case, right? And so there is, of course, a trade-off there. I could, test this with every single error category and every single error severity, but that's like, that's hundreds of combinations. And I'm not going to do that because, testing it with a few increases my confidence enough that this kind of simple function that just puts something in a database works. So let's break this down into the 3 main stages of testing. So when you think about how to test code, you first have to think about how am I going to get to the point where I can actually test the function or the class or whatever I have that I want to test. So that stage I refer to as initiation. So this is setting up the state in the program required to even begin testing. So in this case, I'm using these function parameters here to my test function that starts with the word test. So in these parameters, the testing framework that I'm using, which is called pytest, which we'll talk a little bit about in a second, sets up some state for me with these test servers using other functions that I've written. So what this is it's a fully built web server that I can interact with just to test with. So if you're testing a numerical program, this initial state may be something like, if we go back to the numerical integration example, maybe the function that you want to integrate, the bounds that you want to integrate, right? In my case, it's a test web server that I want to interact with in database servers. So when we run the code, the next stage is called running. What we do is we actually take the function that we want to test and we run it, right? We go and see what happens when we run it. In this case, I'm logging stuff to database with the log to database function. Numerical integration, you would maybe go and integrate some test that the function that you set up in initiation, like let's say it's f of x equals x between your bounds, and get the result, right? And we store that result. In my case, I'm storing it in the database, but you could easily store this in a variable. Then the final stage, and this is really the most important stage, is assertion. We test the results of our test program against some known value. So in my case, this is checking that the stuff got into the database. The numerical integration example, that would be testing some function that we can integrate by hand against the expected value. So if I integrate f of x between 0 and 1, I can just go and calculate that on paper. I can test my numerical integration scheme value against that. Now, of course, you do have to be careful there, because with any numerical scheme, there may be some round-off errors. And so you can use things like NumPy is close to test within some error bounds that you find acceptable. So how do we actually run these tests? So I am a big fan of this Python testing framework called pytest. The concept of testing is entirely language and framework agnostic, but there are these things called testing frameworks that help you. And depending on the language that you use, there will be some other framework. Pytest is really great for Python. So here's their homepage here. So what does pytest actually do for us? Well, one, it collates the tests. It goes and finds all of the tests in your code. How does it do that? Well, one, you can give it a path to see where all the tests are, but two, it just looks for Python files that start with the word test, and it also looks for functions in those Python files that start with the word test as well. So it provides a bunch of useful features as well. So fixtures are a very useful feature of pytest that you may want to look into if you start doing some advanced testing. That's where those test parameters to the function come from. Those are pytest fixtures. Handles the running of all of your tests, so it runs them and it makes a nice little kind of spreadsheety looking thing that tells you whether they passed or failed, and it also allows you to debug tests. So here we're just going to run through a real production repository that I have that has tests in it. So you'll see here in tests, in the folder tests, alongside my code, I have a folder called tests, and in there, there's a bunch of other folders that contain tests for the specific parts of the code. And all of those have files that start with test, 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 test. And in each of these files, there's a bunch of functions that all say test something. Then in here, we also have coverage.py. This conf test allows you to configure the test. So it is kind of configuration for pytest itself, and pytest will look for that file. So let's run pytest. And we do that just by typing pytest once it's installed. It's a Python package that you can pip install. You'll see it'll go through, and each of these green dots mean a test passed. So it goes all the way through. And at the end, it'll tell me, okay, all of these passed in the time that it took, 11 seconds. And I also have it printing out some temporary files that I used during the testing process. Okay, so passing tests is great, right? Like, okay, my code works, excellent. But what happens if a test fails? So tests can fail if you fail an assertion or your code raises an exception. So what I've done here is I've gone into the main code base that's being tested here, and I've raised an exception somewhere that was unexpected. So let's see what happens when we run that. So now I run pytest. And everything's running, but I start to get these Fs here. And so a bunch of the tests are going to fail because of that exception. So pytest also prints out the traceback. It'll tell you what went wrong in your test and potentially in the main code, depending on how it's being tested. So you can often just figure out what's wrong from that. But if you need to run the tests again, there are a couple of things you can do. You can, sorry about that. You can run just the test that failed using pytest -x. So pytest -x will stop the execution of pytest at the point at which it first fails. See, that failed much faster. So if you have lots and lots of tests, it's often helpful to do this so you're not sitting waiting when you know there's a problem already. You can also use pytest --lf, which will only run the test that failed the last time. So that's, again, very helpful when you have lots of tests. And then, if you're feeling really adventurous, you can drop into the Python debugger using --pdb. So when you use --pdb, it will drop you into the Python debugger at the point where the test failed. And you'll be able to do things like inspect the code, inspect variables. And you'll see here, I just raised this exception, and that caused a problem, right? The code crashed. Okay, and then you can quit that as usual. So this is how you can debug the tests. And I obviously can just go in and remove this exception. Maybe a little bit more complicated in a real case, but this is how you can interact with pytest to figure out what's wrong. Now, the next question really is, how do we know that we're doing a good job of writing these tests? Okay, obviously, you have to start small. You have to start testing one thing. But one metric is really kind of evolved as a good metric to track how well you're doing. That's called code coverage. So in Python, there's this thing called coverage.py, which allows you to track code coverage. And what code coverage is the fraction of lines in the host program that are executed when you run the test suite. So this is going through and counting up every single line that was actually ran by the Python interpreter during execution of the tests. So high test coverage is fine. This is good, right? Generally a good thing, but it doesn't necessarily guarantee that the code is correct for the reasons that we talked about before. You can have 100% coverage and still have bugs in your program because of things like unexpected parameter types and so on. So there's a plugin for pytest called pytest cov, which runs code coverage automatically for you. So you just run pytest --cov, and that will give you a coverage report. And then you can run pytest --cov -cov report equals HTML, and it will make this web page for you. So let's just have a look through this web page. So you can see that my main code coverage is 88% here. And each file on the right-hand side here has code coverage tracked individually. So let's go in here, and you'll see that some of the lines are highlighted in red. And this implies that I didn't write a test for those lines. We look at something a little bit more complicated. Here you can see that I never failed a transfer. I never used this function fail transfer during the test phase. So why is that? Well, it's quite difficult to make something fail in these kind of clean test environments. So I'm going to have to come up with a better way to test this code if I want to increase the code coverage. So code coverage is a really good way of tracking exactly how well you're doing when it comes to writing tests. So this is all well and good, and you can run pytest on your main machine. But if you're working in GitHub with lots of people, it's often helpful to have the tests run automatically within GitHub itself. So this on the right, this is the configuration file for a GitHub action. Now, what GitHub actions are the little code snippets that you can run on GitHub's machines when certain things happen. So when someone pushes to the repository, when someone makes a pull request, this configuration file will tell GitHub that it needs to go and get a server and run this stuff on it. So what does this actually do? This sets up a job, which is called test, which runs on an Ubuntu machine. It has certain steps. These users are effectively like packages that you can import with GitHub Actions. So I'm saying run this on Python version 3.10, and I install the Python package, and then I run pytest --cov. What will happen is every time anyone pushes or creates a pull request, this GitHub action will be performed. But how do we actually see what happened with this? Well, you can see here that you can go to the Actions tab in GitHub, and you can see these ticks tell you whether or not the thing failed. If it failed, it will be a cross. You can see from my commit messages here that something was going wrong, but I was passing all of the tests all of the time. So this is kind of, okay, high code coverage does not necessarily imply correct code. So what was happening here is that we were trying to run on a new machine, and that machine had permissions levels that were not what we were expecting, and we couldn't write files where we wanted to. So I had to modify the code to fix that. So all of the tests were passing, but when I was trying to run the code, in a real world case, it was breaking. So there are a couple of things you can do. Obviously, you patch it as quickly as you can in the meantime, but you should really go back and write tests that test that kind of edge case that you weren't considering before. But let's see from a kind of pull request world, what happens here. So what I'm going to do here is show you a pull request that has already been merged. So this added authentication to the system. So you can see, I'll zoom in here, in this initial commit, all the tests failed. And you can see that from this little X here. And then we added a bunch of extra stuff, and the tests began to pass. So this included adding new tests and adding different features to the code. So you can see they failed here with the X, and they all passed with the tick. And you'll also get an email if you've signed up to the notifications correctly. You believe they're on by default when the tests begin to fail on one of your repositories. Okay. So the next kind of nicety to have is a thing called automatic formatting. So there are many tools for many different languages that allow you to automatically format code. So in Python, a very common one is called Black. And there's another one that we're going to talk about called isort, these two different things. So on the right here, I have some quite poorly formatted code. You see that this is valid code, it will run, but this list is kind of raggedy and doesn't look right. And there's a space here, but not here. And so I can run an auto formatter called Black on the file. And what that will do, so it's a command line tool. So I say Black, my Python file, it will take that file and reformat it in a standard way. So you see the list has become normalized. There's nice spacing everywhere, and it just looks a little bit nicer. So I also up here have a bunch of imports. Now, there's a thing that we can do called sorting these imports using a tool called isort, which will put them in a standardized order. So I'm now going to run isort on this file, and you'll see to put all of these standard library ones at the top. There's a space in between, and then external packages come next. They're all sorted in a standardized way. So if I go and I put this back to how it was and I run isort again, I will get this exact copy back. And it's the same thing with Black. If no matter what I do to the code, as long as it is still valid Python, it will reformat it such that it looks the same every single time. Now, why is this at all useful? Okay, let's say I make a change to the original code. So this is the diff. So green lines are lines that have been added, and red lines are ones that have been removed. So here it looks like someone's added matplotlib as an import. They've added numpy as an import, and they've added the sys library as an import. But down here, they removed sys, and they removed numpy. So I think what they've done is they just reorganized these imports, but maybe they definitely imported matplotlib, which wasn't there before, right? That's a kind of unique add. And down here, they moved the middle. Okay, so hello. So this list now, it's a little hard to read, but I think what they did is they changed this middle element to 3. But you'll see that this diff is very hard to parse. And when you submit code to a repository and someone comes to review it, they're going to have to do this parsing, right? They're going to have to read the code and figure out what you changed. Now, if we use an auto formatter on the code all the time, before we make commits, what we'll do is we will make sure that those diffs are only actual changes to the code and the way that the program runs. So here you can see I used isort and Black on the files before they were committed to the repository, and before I committed the changes. You can see, okay, the actual change that they made is they imported matplotlib. Down here, the difference between hello and 3 is highlighted. And in this little silly example, I was able to work it out, but because formatting changes don't change the execution of the code, we want to highlight the changes that actually do change the execution of the code. And it's very easy to accidentally make large formatting changes that create huge diffs that are then very hard to read when you're reviewing the code. So You can run all of this stuff automatically on your computer before you make a commit using a thing called a pre-commit hook. I won't go into very much detail, but this is something you should certainly look at. And here is the example for running black and isort. So this is the configuration file that you put in your repository to do that. But I'll let you look that up on your own. It's relatively simple, but you just need to kind of copy and paste some files and do some configuration stuff. What that will make sure is that every time you make a commit, you know it's formatted in the exact right way. We can also create a GitHub action that goes and checks that the formatting is correct when anyone makes a push or a pull request. What this does is this runs black and isort in check mode. And it will, if the code is not correctly formatted, it will raise an error and we'll get a tick next to that commit. We'll get a cross next to that commit, sorry, until it is correctly formatted. And this is really helpful because this makes sure every single commit in your library has been formatted correctly. Okay, so let's talk very briefly about documentation. So this is starting to get into the ease of use world. We've made sure that the code is correct through testing as much as we can. But now people are going to have to use the code. How do they figure out what to do? Well, there are 4 main classes of documentation. And the first one of those is you. Right? And you want to avoid this as much as possible. Okay. This is people coming to you and asking you how the code works, what it does, and how to use it. If your code becomes at all useful to anybody, this will begin to annoy you significantly. The other problem is that you're very lossy compression, right? You forget things. We all forget things. When you come back to your code, you'll have to remember how it works and what it does. Now, if you're a starting graduate student, you don't have lots of code sitting around already, you know, you'll remember it all, but trust me, by the end of your PhD, you will have forgotten what all of that code does. So the next level of documentation is comments. And I think the main thing that I want to talk about here is how to write useful comments. So not all comments are useful. In fact, a comment that is like factually incorrect is the exact opposite of useful. It's very, very unhelpful because it will make you think much more about the code than you need to. But even if it is correct, they're not always actually helping us. So if we go back to this function that we wrote before, so I've added a comment here that says create a list of 3 items. This is a kind of comment that is somewhat common for beginning programmers. This comment is entirely useless, right? I can very clearly see that this is a list of 3 items anyway, right? I can improve this by talking about why the object looks like it does instead of how. So here I've explained why the middle value is a value of 3, and that's because it's used as a return code of the process. Now, this is kind of weird, right? Like, what are the other hellos? What does my function do? My function is probably not a very good name. So actually, the code itself is at some level part of the documentation. So I can do a thing called refactoring where I take this function and I don't change its kind of use. I don't change the stuff that it does, but I change the parameters and the return values in such a way that it makes more sense. So I can change that function to just to be this. So I called it 3 adder and return because it adds 3 to stuff. It still takes hello as a parameter because maybe that's a an important variable name outside of the function. But you can see I've added a type annotation implying that this hello should be an int. I said that it returns a dictionary of strings and integers. So these type hints are also part of the documentation. They tell you the expected input and return values of the function. Now then at runtime, they're not actually enforced, but they are a key part of the documentation. And I now return a dictionary that has a return code of 3. Left is hello plus 3, right is hello plus 3. And this makes a little bit more sense, right? this is a much more useful way to understand the data that we're getting out of the function. I could have added a big block of comments explaining that this is the case, like I did before, but actually this code is now shorter and it's easier to understand. If I want to be even more precise, I can use a library like attrs, or I can create a class, or I can use this library called pydantic, which actually enforces these type hints. So this left must be an integer, right must be an integer, return code must be an integer, and it's by default 3. And I can create this class here that return, so that is the return value. So I say 3adder and return returns an instance of 3adder. That's what I do here. So left is hello plus 3, right is hello plus 3, and the return code is 3. So this is kind of like the dictionary, but as you know, dictionaries can contain anything. You have to make assumptions about what they contain. If I have an object, I know exactly what it contains because that is how it was defined. I can get a little more object-oriented about this and move that function into a class method of 3adder that returns an instance of it. It's a little bit more advanced. If you know about object-oriented programming, this is for you. If not, just have a think about the ways in which the return values of your functions and their types can enhance the way that you understand the code and the way that it works. Okay. In Python, it's very common to document your code using docstrings. So on the right here, this is the NumPy documentation. I'm sure you've used this. It's excellent documentation. It tells you tons about the function. So docstrings generally tell you parameters, return values, and the exceptions that the function may raise. And this is very important in Python because functions can raise all kinds of exceptions, and you may need to handle those. If you have a scientific piece of software that's making a single figure, it's okay if it crashes. If you have a very large application, you do not want it to crash unless something really bad happens, right? If a function does something wrong, you may want to catch that exception and do something different instead. So having a documented list of the potential exceptions that it can raise is very helpful. So actually, all this NumPy documentation is just the docstrings, but turned into a website, and there are plenty of tools that help you do that. So if you click source, you can actually see that the docstring is here. So it's just written out like this. So NumPy has its own style guide for docstrings. And I would very strongly suggest that when you write a docstring, you make sure that your docstrings are in the NumPy style. So writing docstrings has become a lot easier in the past year. If your code is if your code in the function is well documented, there are actually helpful comments saying why, and you've used type hints up here. The large language model tools like the GitHub Copilot, if you're comfortable using them, really makes it easy to write these docstrings. So I just pressed tab here a bunch of times, and it made a relatively nice docstring. And even in very complicated scenarios, I've had great docstrings be automatically created by the large language models. And I think this is really one of their key uses. They're very good at this. They're not very good at lots of things. This is something that they are very good at. Okay, and then the final piece of documentation is narrative documentation. So there are many ways to do this, but what narrative documentation does is it's kind of like a book to tell the users how and why to use your software. So a common platform for storing these is called Read the Docs. And I have a few packages on there. One of them is SwiftSim.io. So this is a IO library for working with particle data. I'd encourage you to just go and check this out. Just have a quick look about kind of what's going on in here, what kind of things we talk about. So in this documentation, we have all kinds of things like how to make plots, examples of what they would look like, how to read data. We have some example data you can download to play with if you haven't ran a simulation of your own yet. We have all kinds of stuff in here telling you how to use the code and why to use the code. Docstrings are great, but when your application gets very large, people aren't going to be able to read through all of your code. They're going to need to know where to go to do the thing that they want to do. SwiftSim.io does tons of things. It loads data, it allows partial loading of data, it does visualization, it integrates with structure finders, it can create initial conditions. And someone's not going to be able to figure it all, like where they need to go from just reading the code itself, because there's, hundreds of files in there. And that's where the narrative documentation really comes in useful. Okay, let's get on to the thing that everybody loves, which is talking about speed. Optimizing code is very fun. It's not a simple task, because it really requires knowledge of both the problem that you're trying to understand. So in the physicist case, that's the underlying physics, and the computer science of how the computer works, what it's doing, and the best way to optimize things. I'm not going to talk about how to optimize code. I'm going to talk about the process of optimizing code. So there are two major things to keep in mind. Never optimize untested code. The problem with optimizing untested code is often if you do something wrong, the code will be much faster. Right? It's very easy to get performance gains if you give up on getting the right answer. So it's very helpful to have tests that you can run that tell you whether the code is right. The other thing is writing tests gives you something to profile. Now, what is profiling? Profiling tells you how quickly the code is running. So the simplest of that is pressing go and starting a stopwatch. If you optimize the code, the number on that stopwatch should go down, basically. The test gives you something to test that with, but also it allows you to use profiling tools. So a common one to use in Python is called PySpy. This is a really excellent tool. What PySpy does is 100 times a second, it stops your program and asks, where is the program running? Which line is currently being executed? This is called a sampling profiler. What this allows you to do is build up a histogram of the lines that the code is stopped on. And lines that are used more frequently, that take up more time, are more likely to come up again and again and again and again. And we represent that in a thing called a flame graph. I'm going to show you an example flame graph of the code that makes this image. So this is an image from a simulation. It uses radiative transfer to kind of pick out specific gas densities. So it's a quite complex process doing radiative transfer. And so I initially expected that the majority of the time of the code was going to be spent doing the radiative transfer bit. I think it comes out to be true, but it's still surprising. So let's take a look at the flame graph for the code that made this image. So along the top here, we start out with the entire execution time of the program. And that's broken down into functions that are called at the top level of the program. So, and it also tells you what line this was called. So here, transfer.py 100, line 100. This is the part of the code that does radiative transfer. And why is it called a flame graph? Well, it kind of looks a bit like flames. More complicated ones look more like flames, but you can drill down here into the call stack. So if this function called another function, called another function, called another function, called another function, that's what this drop-down thing here is. So the radiative transfer here takes about 70% of the code execution time. Actually, this line here, 113, is saving PNGs. So I can't optimize that anymore. That's kind of out of my hands. This line here is taking the log 10 of some data. That's optimized by NumPy. I can't fix that. This here is taking a standard deviation. Again, I can't optimize that any more than it is already optimized. I'm just using the NumPy function, which has been optimized by somebody else a lot, right? It's people's entire livelihoods optimizing these numerical methods libraries. And so actually optimizing my radiative transfer part, the part that I wrote, is only going to save me, even in the best case, probably about 50% of the execution time of this program. I don't run this program very often. So that's a complete waste of time, right? It takes about 30 seconds or a minute to make that image. And taking that down to 15 seconds or 30 seconds, that's not going to change my life, right? If it was taking hours, then this would make sense. But the flame graph and the profile gives you the information that you need to know to tell you whether or not it's worth optimizing programs. And it also tells you where to start. So I'll go back to that key point. do not attempt to optimize a program before profiling it first, because I may have spent all of my time trying to optimize this line because I thought it was the worst. Optimizing this entirely away is barely going to change the execution time of the program at all. The final thing I'm going to talk about very briefly is packaging your code. So the packages that you install, all the code on your computer, including the operating system, they were all written by humans. It's very easy to start out and think, oh, these things are kind of magic, right? Where did they come from? I do pip install. Where does that come from? Well, when you pip install something, pip goes and asks the Python packaging registry for a package of that name. This is a public registry. Anyone can upload anything they like to it, as long as it, complies with some very basic rules. And you too can release packages on pypy. What will you need to do to make a package? Well, you'll need to write down the requirements of your package, who wrote it, in a metadata format. And the one that people use these days is called pyproject.toml, T-O-M-L. This is a very well documented piece of code that you will have to write that describes your package. Here's the one for the code that I was talking about before. So it uses this build system. Here's where the packages you should exclude. So the tests are not a package that you should be able to install. Makes sense. Project name, the dependencies, these are the packages that I need to be installed to be able to run my code. Some information about me and other people who wrote the software. And then all the way down at the bottom, I can configure the tools that are used as part of the project. So pytest, I configure pytest here. This tells pytest where the tests live. I can configure the code coverage plugin. Code coverage should only track the files in these folders. Also, you can add some additional configuration. I also configure isort, and I also configure black here. So pyproject.toml is a really useful way to describe all of the metadata around your project. If you're interested in writing a Python package, I think it's a really good place to start, because the resources that tell you all about pyproject.toml will also tell you what other files you need and exactly how to get things to work. And then it will also talk about how to upload your package to pypy. Okay, and with that, I have a few exercises for you to give a go. You can take your code and you can apply the automatic formatters to it. You can pip install black and isort. They're super useful. I would say run black first and then isort. You probably want to configure isort to play nicely with black. There is some information in the documentation on how to do that. You can write some tests for your code and run them using pytest. Give a GitHub action a go if you're already using GitHub repositories. It's very useful to have the tests run automatically, or even just have the auto formatters run automatically. And then try profiling some of your code. I think this one's actually really fun. If you've never done it before, PySpy is very easy to use. The flame graph is just a SVG that you can open in your browser. It's super interactive. You can click around and see everything. I'd give that a go, and maybe it can kind of give you some insight into the code that you've already written. So thank you very much for listening. If you have any questions, please let me know. Thanks.